Hello everyone, today we're doing Advent of Code and starting from day 15 because last time I believe we ended up on the day 14 and about when we found this nice uh, Christmas
Christmas
tree.
tree Easter egg, yeah.
Yeah, tree Christmas egg, where is this? Yes, this is the tree that we found last time. So, which means today we're starting from day 15 and we're gonna do it up to day 22. I believe I all caught up, so there is no new title, no new challenges yet. So day 15 was the last, the next is. So it's all about mazes, right? So warehouse walls. So what it was all about. So it's like again, you can have some kind of map, and I guess you just uh, allowed to move around, and you have like do you have some picture? At least one. Should make a picture. We have at least one. This is some kind of map. Let's make it. Let's turn it into array plot. I don't know where I did this. So I think this is like some kind of wall. Make it black. Uh, this is where you're allowed to work. It's white. Right, and there's some kind of blocks that I think you're allowed to move around. We can make them red. Not like this red. Like this red. Maybe blue. Right, and I think you start at some position over here. We're gonna make. So you are kind of some warehouse worker moving around blocks, and you're allowed to move them. Like you're given like this map of all the initial position of those blocks, and you're also given a path that you take. So basically move left, right, uh, up, down, and so on. Starting from some initial position, you have some moves, and the move essentially you just code up the move, right? This is the move that you do for the first part, right? This is just some simple way of encoding how you move the block. And I think the difficult part is because the block that you move also moves the block above it and so on. So just that's why there's a nest while. So you move all the blocks until you hit the free spot. So it's basically like a game, right? Hold on, let me this work. Let me come on. How do I come? How broken? Yeah, okay. I reproduce this answer, so it must be. Oh, I have a manipulate. That's a good one. Oh, cool. Yeah. So basically, running around, moving blocks left and right, and you do it for all the given number of steps that is just given to you, right? And then after you do it, you just look at the map and compute something. I don't remember what. Just the number. I know some weird number anyway. That's not important. I think the next one was more weird because now you also widen the map, so it becomes just more annoying to implement it because now you have again some data, but now it's on the newer map. This will actually take some time to run. Oh, I also have a manipulate here, so it's not a very good solution, I guess, if it takes so long. But I don't believe it was so slow. Yeah, like less than 10 seconds, so it's fine. So we have just the same setup, but you have wider boxes. So you have like a left and right box, which you indicate by these braces, left and right braces. So you widen each box, so your screen becomes wider. Hold on, I wonder if I just make this aspect ratio 1. I think it would look nicer. Yeah, like this. The player is now like a thin object, but it's again like moving around and pushing boxes around like this. The boxes are wider, so it's like more complicated logic to push them because but essentially the same problem, right? You again compute the same number, you get the result. I know, not so interesting, but was kind of challenging just as a general coding problem. And okay, day 16. Again, some kind of maze. A lot of mazes this year, right? there's some kind of reindeer running around on the maze like that. So you're given a maze, right? So where you start? Oh, you start. You have a starting position at red, this left bottom corner, and this ending position at right up corner. So usually I solve this mazes like you can just make a surgery of the grid graph, right? As soon as you have the dimensions, you just make a grid graph. It's very easy. This is like a big one. Let's make it's just rendering. It takes a while, but usually don't render it. So this is just a smaller version of it. So we start with this grid graph and make some kind of surgery of it by deleting edges that are not allowed on the maze, right? So that you can turn this graph into a maze graph, right? So that's where this graph construction is happening. So you construct this again. Let's make order. So after you construct this graph, well, it's too big to render, so but you don't have to, I guess, to worry about it. But this one is also a weighted graph, right? There's also some weights involved because the deer that is walking around in this maze have a number of points assigned to it, whether it's making a turn in that maze or not. So you're not just required to solve the maze, but you're also required to solve this in less number of points, right? To get the best score, basically. If you make a turn, it costs 100 points. If you just move one step, it just costs 1 point. So we need to do it in less number of steps. So it's kind of optimization, but you just make a. So here you're basically constructing all the weights. So I turn this graph into a weighted graph, right? Because I turned every edge, depending on whether you turn or not, right? If it's like here, it's like basically very simple. If you going up, what's this? Right? If it's the same, then it's costs 1. If it's not, then it costs 1000 plus 1, right? So that's how you can weight each of the edges in the graph, and you compute all the paths. Now the paths are already automatically incorporating weights into account, so it's actually shortest by summing all the weights along the path. And then there's actually just two solutions, because there are two solutions because you don't know a priori whether do you want to end at the final destination from bottom or from left. So the point was to actually encode the graph both by also incorporating the positions of it at each point. That's why the grid graph is so large, because it's not just this graph, but also each of the points in the maze are duplicated for each possible orientation of the deer in that maze. So it's like this number times 4. So right. So width plus times height times 4. That's like how many vertices are in the graph, but edge count is even larger, right? How much edges there? Yeah, that's a lot. So you just in order to compute the shortest path, you just check both of them, whether they end up like going from below or to the left, from the left to the final destination. Just compare which one is the. Turns out this is the shortest, right? So I just compare both of them and just compute the length of that one, right? And for the second part, you basically do the same kind of thing. Just you're not just looking for the shortest path, a single shortest path, because that's what you're gonna find shortest path produce. Just a single path from start to the end. But you need all the possible paths, shortest paths, right? So they may be overlapping some. There's some ambiguity can be in the maze so that you can maybe turn a little bit, explore slight different trajectory, but you still end up at the end reaching like with the same score. And the task was to find all the positions you would explore that way. And just essentially gonna be the same path, just a little bit widen. Right? I think this is like if you look at stare at it like this, I think it's like the difference right? The only difference in the whole maze, if you stare it a little bit, it basically means that here you can do any of these two corridors of your choice, and you're gonna reach and also here, because there are just two choices to make. And I found it using what? I know, some like straightforward computation again on the weighted graph. I think I computed all the distances from start to all the points, so I have them to all the possible ones that you can reach, right? And as soon as you have those, you can use it to extract the costs and do some basic traversal. I don't know. So you start, I'm like backtracking, I guess. I'm a bit. I don't remember how I exactly did it. I like starting from the end because I know the shortest distance, right? I can prune. In the first part, I computed the shortest distance in number of points, right? Then you basically, in order to find all of them, you can backtrack. So I did it manually, just using some nest while. If this is the limit, I'm backtracking from the end point and computing all the moves that I can make, right? Looking up the idea. What is the idea again? The idea is like a weighted vertex. This is like all the possible, it's all the vertices, and this is the position of those vertices so that they don't have to recompute it. This is like I make an index of all the vertices so I can look up it quickly, right? If I found it, I extract the distance to that vertex, compute the cost. Here just this check whether you make a turn or not, right? Something like this, blah blah blah. Yeah, and I do it for all possible moves, concatenate those, and that's yeah, it's just like some kind of backwards breadth first search for all possible moves. That's how you can discover all these branches without going too far so that it would be computationally difficult, because just basically because you can prune by the limit that you already computed in the first part. I also made this animation, I guess. I made it before I've solved it like this way, which it was efficient enough. Just understand what to do. Like you just, this is not the backtracking. This is how you would explore all the paths, right? So that's how I show the deer just walking everywhere. And as soon as it reaches the cost that is like larger than the limit, it just stops. So that's how it's not very exponential. So we can always stop it there. So here just basically this check. Yeah, and then you're just filling up the costs, which is the array of all costs for each point in the maze. And the animation is pretty slow, and this is what this kind of exploration was too slow. I don't know what this was much faster version of it. Anyway, so that's the deer maze. How's it called? The reindeer maze. All right. Okay, day 17. Well, that was a kind of fun one. I remember. So essentially, you are tasked with coding up a simple computer which just has 3 registers and a bunch of instructions. This is like an assembler with 8 instructions like this. So I just have to call them up. Right, this is just a parse. I'm just parsing it. So you like given some initialized register A. This is the program, which is just a list of calls that you have to run. So there are 8 possible codes from 0 to 7. Here's just an implementation of those. It's just most of them is just some bit operations, right? For example, like code 0 takes the register A. Then there's like some weird way of specifying how to do the argument. So this is like the code. This is the argument to the code for, and that's that two different types of arguments. Right? That's how you just encoded the combo argument and the literal argument. This is just whether you take the operand for as given or you actually look up the some other register. So this for actually means if it's a combo argument or combo operand, I guess it was called, then you have to look up the register A. If it was 5, you would have to look up register B, 6C, and everything else just take the operand as it is literally. Right, so just a straightforward encoding of the problem of the instruction set here, just an association that operates on another association of registers like this, right? Or I guess the state, you just encode the state as the state has 3 registers, the program itself, the pointer, right? Because you kind of allowed to jump here. Like I think this one is the instruction that allowed you to jump around on the program. If register A is 0, you don't do anything. But if it's not, you change the pointer to the literal operand that is given to this code. Like I think this is 3, so at the end you see that you are jumping back. So you kind of you immediately see that this program is some kind of loop. You do some operations, then you have a jump to the beginning of that program, right? Maybe for the first part you didn't have to understand what this program is actually doing. Or you're given a bunch of tests, so it was a bit annoying to make it all those implementations right. So all the tests here just checking whether those are true, and then the task was simply to run this on the initial state like this that you're given and turn it into a string and see what is the output is, because you have this output list. Only a single instruction that appends something to the output here, right? So the instruction number 5 appends to the output the operand combo operand mod 8. So just a digit from 0 to 7. So that's what the answer to the part 1 of the problem was, just to produce the output of the program. But the second part was a little bit more challenging, so that's why I like it, but still kind of annoying because you had to actually understand what the program was in order to optimize it, right? I actually had to go through this list and see whether I can optimize this machine, because the task was to find this number. So this number is now not important as you are given it. You have to find a different version, different A register that you have to initialize your state into, so that your program, the same program, outputs the program itself. So basically tasked with finding a coin as an integer. So we're given a program, not the coin, but like the input to the program, so that it becomes a coin or something like that. Right, so we're tasked with finding this A, and here I spent some time to actually just optimizing this thing, right? I actually compiled it just to see how fast it runs. Then I realized it's all hopeless, because if you actually read the code and what it's doing, it's producing a very basically all the outputs that the program produces depends on this A, because whatever the program is doing here, I try to decipher it. So that's actually like a more human readable form of that program. What it is doing is basically takes A, stores it in B, then shifts A by B number of bits, right? And stores it in C, and then it produces the output. And then it just decreases A by some kind of shifting it. That's how you decrease it. Shifting A by 3 bits is equivalent by dividing by 8. But that's like just a loop, and you just go through this loop. This was like a loop like this. Alright, so that's like how the program worked. So you immediately know that it's just a program that outputs something on each iteration, right? But the point is that each output depends on how many on the fixed bits in the A. So we can essentially find the A that produces a given output by just finding all the bits of A, like in some sets of bits or something like this, right? and because you're shifting it by maximum 7 bits, because you always whatever the 7 essentially means that you just take last, if you XOR with the 7, you basically take just 3 last bits of A. So it's maximum, again, the number from 0 to 7. So the maximum shift that you can perform on A is 7, so you don't have to look farther away than 7 bits. So in a way, or in total, because you're given 3 and you're maximally shifting by 7, maximum you can look up, the dependency is like 10 bits. So that every output depends on the 10 bits of A, something like that. Right, so it's actually a bit complicated. What all I had to do is to make this table. I think it's just all possible 10 bits, so there are not many, right? So 1000 bits, 1000 possibilities, right? For all of those, I can determine what output it would produce, right? This is just the same thing encoded more directly. I guess how each of the output depended just by reverse engineering that program here. So you just make this table, and then what you do is just typical recursion, right? So in order to solve for any output, here we want the output that produces the program itself, right? So in order to solve the program itself, we just do uh, essentially like trying to find, looking at the table where we find, selecting in the table all the possible ways to produce this output, right? And then just stripping away this suffix, because it's always going to be 3 bits long, right? As soon as it's not the solution that the output that we're seeking, we're just dropping it, right? But and we just, as soon as we find the first one, because we're doing the breadth first search, the first ever solution that is found, basically when we're gonna exhaust the output, right? That's, we just return it immediately here as an integer. So the solution that we accumulating is just the bits here, right? Yep, and we just return it, and I believe it was pretty fast. So we just, yeah, so it's immediately returns, and you can see it's a giant number. So if we were doing it using brute force, it would be very complicated. Even though even it would take like a what is it, like 100 nanoseconds to try one try. It still would take a while to find this number if we were doing it sequentially. Maybe like parallelizing it across many cores or anything, something like that, but still would be hopeless. Here just checking that the compiled version of my machine actually produces the program here. Yep. Kind of fun challenge. Not a great fun because you had to understand what it's doing. So it's kind of not input dependent. That means that every participant got the same input, I guess, because there is no much wiggle room to change the program. You always get this kind of program as an input. So I believe everyone got the same number at the end. Anyway, next, up next, day 18. One. Okay, let me just remind myself what's happening. Oh, this is again some kind of maze, but the one that you construct by. Okay, so we're given. Again, now it's like a small one. So again, it's a maze. Basically, you're given a maze as a graph. So again, I'm doing the surgery on the grid graph. Like a given number of bytes. What are the bytes? This is the old possible. It's like some kind of bytes falling down the sky into the grid graph, trying to block the exits or something. That's how the walls are constructed in the maze. It's just sequentially by falling at different positions in this grid graph, right? That's why the first part was to take 1024 of those. That's what, after taking those number of walls, that's the kind of grid graph you construct, and then you just simply do the shortest path in this graph. That's the highlighted solution, right? There's some walls here, but basically you're allowed to move freely. There's no points like last time. It's just a different version of it. Yeah, I guess the problem was to compute the path, the length of that path, right? And for the second one, very similar one. Again, the graph, and here just what was the problem again for the second? Hold on. About to grab more of the bytes. Oh, it was you're given more than 1000, right? So it was a bit challenging, but maybe not really. Well, I get a bit more optimized. Here we should naively we should have like computing the shortest path for every possible graph that you construct after each additional byte is added, because like as soon as you add one byte, you can block the path, right? So in a way, you have to recompute it. So maybe it's not very efficient to run the shortest path algorithm under the hood. So here it's a little bit, well, it's basically the same. It's just more efficiently constructing graphs, I guess. Just deleting the edge. So it's like a direct surgery of the graph. You start with the grid graph. I'm only like replacing all the vertices with like a grid with the grid vertices. So it's like two numbers, right? So you're starting with and just folding over all the bytes you are given, right? For all moves, you delete some edges around it, and you stop as soon as the graph distance is like not is actually possible. So it's like the task is to find how many bytes and at which position was the last byte that is blocking the path completely, right? That because at some point there's no path, and it's completely, the maze is completely blocked. So that's just a simple one-liner. I think it was reasonably fast, but maybe could have done better. But anyway, all right. Next one, day 19. Okay, this is like very simple combinatorial type of problem. So given some, let's see, so you are given a list of patterns, and like just of letters. I think that they were towels: red, white, and green. U was white, right? White, white, green, blue, blue, and so on. You have a list of patterns that you're allowed to use, and then you have a list of towels that you want to construct out of those patterns. Basically things, right? For example, in order to construct this towel out of the patterns that you are given, allowed available patterns, you just have to stitch them together, right? If you have you have to find a pattern like this, or like this, or like this, or like this, or like this, like this, right? And then the next one, and the next one. So you just need to find like all the strings from allowed strings that after the joining them makes a new string. So basically that's the task, right? And in order so the naive part here in the first part of it was just making the valid tau function, right? Which is just a memorized version. Memorization actually very important here, is like because you don't have to check whether the tau is valid or not. We're gonna check all the available towns that is there in the search, even the short ones, so that we don't have to look for all the patterns more than once to find the same tau. So that's why we're remembering whether the given tau is we already checked it or not. So that's just straightforward way of selecting all the patterns that start, so that the given tau starts with that pattern. So that's the virtual the available patterns, and then we just recursively check whether from all the available patterns, whether they are valid or not, whether we just strip away the tau with that pattern is valid, right? So that's very straightforward way to checking the towel, and then we're just counting how many towels are valid, right, in the given list. The second part was more difficult because now you had to not actually just check whether you're allowed to construct a given towel, but actually count how many ways. Again, it's like the naive version of counting is not going to work, right? If you just could try to find all of them, because you're obviously going to get some giant number. So it's again some combinatorial solution with memoization, with then some basic recursion. It's like an empty towel. There's only one way of constructing an empty towel, something like that. And the number of way of constructing an arbitrary towel is just basically the same kind of check here. Again, selecting all the towels, all the patterns in the prefix of the towel, dropping it, and counting all of the cases there, and then just summing them up together. So that's how we count them in this recursive manner. It was pretty fast again. Find it. Yeah, not a big problem. Right. Up next. Race condition. So again, a maze. Already we have to be used to mazes at this point, right? As usual, basic strategy. The maze, turn it into a graph. Find the path. Right, that's the path. I think you're starting from this point, ending up in there. So specifics of this maze was there's actually just a single path, right? So there's no like forks in the road here. So there's no actually problem of solving it. Just you can follow it and find the solution. There's no problem. But basically you're just allowed to find the first part of the problem was to actually find the length, I guess. Right? No, not the length. You're not just traversing this path. You're allowed to cheat in this maze because it was the challenge was called race condition, right? So you're not just going straight through the maze, but you're also allowed to cut walls through. So in the first part, you're allowed to break a wall once. Essentially, you can find a position anywhere in that path over here and just jump through a single vertex, through a single wall to another part in the path, and you can basically making a shortcut, right? And the shortcut's gonna save you some number of steps, and that was the problem, is just to compute all the possible cheats, how many shortcuts you can make, right? This is just me enumerating them straightforward, because the first part was just you allowed only to break a single wall. This is me just enumerating. Basically, it is equivalent of asking all the straight lines of three vertices in this graph that connect two positions in the path, right? So you find those. This is just me kind of very stupidly enumerating. This is a vertex. This is one vertex to the next to it, and another vertex to the next to it, making a line, right? And just checking whether they are all actually on the path here, right? So if the first and the last out of the three is in the path, and the middle one is not. So this is just a way of constructing of all of the possible ways to do it, right? And then here just computing what are the actual savings on each of those, because you know that you're just cutting the path, right? And if you know the position of that point in the path and the position of the ending cheating, ending like at the end of the shortcut, the position of that one in the path, you can just subtract them together, -2. That's gonna because that's how many steps you get to actually make the shortcut itself or something, right? And that's how you can compute how much this particular shortcut is gonna save you. And you just the task was, I guess, to count how much shortcuts save you more than 100 steps, right? So that was the solution. But the second part was a bit more challenging performance-wise, but you still could have solved it. I solved it like naively first, because now you're allowed to break more than a single wall, right? I think the limit was now 10, and I just did it like straightforwardly by given the path you can compute all the distances in the grid. So it's basically the distance in the grid is always the Manhattan distance, just the number of horizontal plus vertical steps, right? And if you compute this distance for any point in the path, which kind of takes a long time because the path is long and this is quadratic, right? The length of the path is like what? Almost 10,000. So square this number, that's basically how many iterations you have to make in order to compute all the distances. And so it took a minute, more than a minute. Basically, you need just to restrict to the upper part of that distance matrix because you're always shortcutting from previous point to the next point in the path. So that's what you basically do by upper triangularizing this distance matrix.
And we have a pause in communication. We'll just give Nick an opportunity to rejoin here.
To make 20 steps through the
Sorry,
walls.
you were gone for about 5 seconds. Maybe just
Oh, yeah. No, 5 seconds, no problem. Just I'm here just constructing the distance matrix from distance matrix for all points on the path, on this red path over here, right? And we just finding the cheats now are all these pairs of points that are the distance for which are less than 20, right? And more than one. So that's all our allowed cheats. So now we can like skip from here to here because there's like less than 20 steps that you're allowed to do. You can skip it a little bit to a different point. Maybe go to here. Like a lot of cheats that you're allowed to do. So that's basically, and this is all of them. Right, and here just this was the flow solution because it took like more than a minute to compute just the distance matrix. But at least I knew the answer, and here just me attempting in two different ways to cut the time a little bit. It's still not it's not ideal, but it's less than 15 seconds, so it's fine. Right? For me, it's like the criteria to actually make the problem correct. You can optimize it further, but it's not really necessary. So here just me, instead of computing all the distances, it's essentially computing the distances, but only in the radius of 20, right? I wish there's just like I think like Wolfram language could have improved this distance matrix thing by just providing an additional argument of the minimum or the maximum distance to look through. So it's more optimal. It's like a more sparse, basically it's gonna produce a more sparse distance matrix. It's like similar to how graph distance matrix works because the graph distance matrix has a maximum distance argument for some reason, right? But for some reason distance matrix does not. It would be very useful. I wouldn't have to write this down, and it would be more optimal. So it's not so like good suggestion for the Wolfram research, I guess, to just implement this maximum distance cut for the distance matrix. So I could have like solved it like this then. Okay, I don't want all the distances larger than 20. So it's gonna run much faster, make a sparse matrix, sparse array of distances. I would just go for it, and it wouldn't have taken so long, right? But manually I have to do it like this, like actually looking around some initial point, all the points, like 20 distances away, to the left, to the right, something like that, right?
Is
And
there
just
is there like a menu option to do a feature request or only for bug reporting?
I guess there is there is a give feedback button. Maybe that is allowed to do. It just yeah, it goes to the side, and you can feel it big form. Yeah, I don't know.
Cool.
So basically, yeah, this is a few versions of the same thing. I'm trying to compute this computes the same number, so it works. Okay. Up next. This is also the fun one. So the here the problem was, it's like you have a numpad, right? And you just tasked with pressing the buttons. What the catch was that you're not allowed to press buttons directly. You have another robot that pressing the buttons, right? You have the first robot that pressing these buttons, but you're controlling the robot by pressing these buttons. So it only like moves like up, left, right, and the A means press the button. Okay, so you basically have this numpad by controlling the other robot that presses this numpad, and you actually have another one that controlling this one, and you have like a chain of robots that controlling each other. That is like a so you have as a solver, you have like one directional pad like this. You press its buttons that control a robot next to you that like moving its arm and pressing a button if you send A to it, and it controls another numpad like this that sends commands to the next robot and so on, right? So you have this chain of robots that pressing buttons, where the last one is pressing these numbers, right? And you just allow and you're tasked with finding like the first part of the problem is just finding all the possible paths that you can take here. Just to simplify it, just make these graphs again. We like graphs. So for the numpad, I made this graph, right? So it just basically shows all the possible transitions that you can do. If I press up, I'm always starting at A, I believe. Right? You always start at A. So if you press up, you go to 3. If you press up, you go to 6. So this is all the possible transitions that a robot, the directional robot like this, is controlling the numpad, and then the directional pad itself also has the same kind of transition graph, right? Starting from A, you can go around. This is all the possible transitions you can do. So this kind of place is not available, right? Because you're not allowed to move there. But given this graph, from first part is just find go to like very straightforward functions like this, just traversing those graphs. For example, if you want to find a path, which is a string, on a given graph like this, what is the positions? Positions are also some pre-computed thing, just the positions of all the buttons, all the characters of the string, right? The positions, all the vertices, I guess, in the graph. So this is just this init press. Oh, it's there just already in the anticipation for the part 2. So this is whether you add A or not, this is for the part 2 thing. But here just find the path. Let me see what it actually is doing. So find the path is just given this string, right? Because the input was just a bunch of those, right? So this string. So you need to press these combinations on the numpad, right? And this is how two robots, what kind of command you have to send to this chain of robots, two directional robots and the numerical robot. I think there are 3 robots in the part 2, in the part 1. Right, this is the kind of string you have to send it there, and I guess you just need to compute some kind of complexity function, which doesn't matter. But the point is that you just have to find this path, or its length, I guess, right? So this is just a way using the graphs to finding those, and because I'm finding all of them, it's not very efficient because it's like you obviously have some combinatorial explosion if you gonna increase the number of robots, and that's what you actually have to do in order to solve part 2, because now we have not just 3 robots but something like 25, right? So finding all possible paths is like completely impossible, and so you have to be clever. And what they have actually done is just code, well, I think this like all this is things that are unnecessary. This is just me trying to solve it in some stupid way, but in the end I just code it up like the solution straightforward again. Breadth search kind of with memorization like before. It's like all the challenges has all the common solutions. They all always involve some kind of search. So this kind of function is very common, right? Memorize the solution. This time I'm memorizing. I guess the important part here. Oh yeah, the important part is to actually construct this function. I guess not used for the solution, but these associations are important. So essentially, what you construct first is all possible ways, for example, on the numerical pad to go through one label to another label, right? So this is all the possible directions you have to follow in order to go from A and pressing number 8, right? Or this would be all possible ways of from starting from 5. How do you press 9, right? Go up, 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 left, press it, uh, press something, go right up and press A again, um, like something like that. I guess maybe it's not correct because yeah, this is the correct one. This is the correct table because we're pressing only the last one. For the second part, I was constructing this association that only this is the starting position and you're pressing this button. So there's always A at the end because A corresponds to pressing the button. But you after constructing this, there's not too much branching points actually. There's always like most of the time just a single solution. Sometimes just for the directional paths, I think there's just one way. Only this combination when you start on this button and you want to press A, then there's just two solutions of equal length. Right, that's the only thing. But on the numpad there's more. So and when as soon as you have more, then finding all paths would become like exponentially more uh, problematic. But given this table, you can just encode this breadth search thing again, right? When you're memorizing the step like this and the depth that you're doing it, right? You're starting at depth 1, depth 0, right? This is just a single check whether I'm starting at 0, then I use either this association or this association, right? I'm extracting all, looking up all the possible strings for that step, and then I'm just recursively prepend A, right, and construct all the steps that are required to reach the next one, calling this search again with a deeper depth, so adding depth plus 1 and adding them up, right? And as soon as I reach depth 25, I just return the string length. That's gonna count. This way, this is just gonna count the all possible ways of actually going yeah, all possible ways of making the combination. Yeah, and the answer was just to compute some number, given that this was also kind of fast, I believe. Yeah, almost instantaneous. So it's okay. As soon as you have a good algorithm with like this, it's not a problem. Right, and the last one, I think it's right. Last one was pretty simple. Today's problem, I don't know, was the monkey market. See, it's like the solution is very short. The problem was, let's see, so there's some kind of monkeys. It's basically about pseudo-random generation. So the most problematic thing to actually implement, to understand what is actually the problem is saying. It's too much text for a very simple problem. It's like you need to make a random number generator, which is basically this function, right? It's like called mix and prune, some bit operations with some modular arithmetic. You do this operation 3 times. This after this after this. That's your random number generator. It's basically you call it like on some number, it's gonna generate another number. If you do it like 10 times on some number, you're gonna generate a list of numbers. So just like a pseudo-random number sequence, right? And the task was just to make it to run it 2,000 times for all the data points that you had. Yeah, there's some lore about it, like there's some kind of monkey prices you're computing, but like don't bother about those, right? So you just computed all of those like numbers, just added them up for the solution. The second part was essentially not too much difficult. Well, this is kind of very cool in the Wolfram language because there's very cool built-in functions to do it, like differences and partition and merging. So it turned out it's just a single line. So this is like very nice one line, I guess. So you also do the same thing. You just compute the 2,000 steps of those random number generators, mod 10. So it's basically the last digits. So you compute the last digits, then you do some straightforward things. Basically, I don't know. I don't want to explain those. That's how. But in the end, you count how many maximum number of bananas that you can buy from the monkeys, something like that. That's the problem. Very difficult text for a very simple solution. But I guess that's about it. The next challenge would be when. Hope it's not gonna crash. In 6 hours. Um, and it's like how many is left? So we have 22, 23, 24, 25. So just 3 days left until Christmas, I guess. And we are done with this year's.
Is the last one on Christmas Day or was it before Christmas?
Well, depends who you ask.
Okay.
It's gonna be, yeah, depends on your time zone.
Oh yeah, of course. Okay, cool. So yeah, that's we could probably do the last three in one go, right? They're not going to be that challenging that you have to break them up.
I don't know. I hope not. I remember that the last challenge is always easy.
Oh really?
It's well, usually. At least there's always a part. There's no part two to the last challenge. Basically, if you solve all of them. This is
Okay.
if I remember correctly, the part two of the last challenge is just basically solve all the challenges before it. So if you solved all of them, you immediately solve the part two of the last one.
Okay. Okay. Cool, exciting. We'll catch you on the next one.
Yeah. Catch you next
Great.
time.
Okay. Bye.